Hey everyone, welcome back to TalkTensors. We're diving deep today into rule-based, conflict-free decision framework in swarm confrontation. This paper, it really caught my eye. Think swarms of robots, like battling it out, making split-second decisions. I mean, intense stuff, right?
Yeah, definitely. What really gets me excited about this paper is, it tackles a pretty big problem. You see, getting swarms of agents, like drones or robots, to work together, especially when you throw in some competition.
Competition, so like we're talking robot battles, right?
Just imagine, like, two teams of robots going head-to-head, dodging obstacles, missiles flying everywhere, and they have to make decisions on the fly.
Okay, now that's a visual. So walk me through this. Why is this kind of swarm confrontation, why is it so difficult to, like, program?
It's like, think about it. They get hit with so much information at once. They've got to do a bunch of stuff at the same time. Imagine you're trying to dodge an attack, but also coordinate with your teammate, all while under pressure. It's a recipe for disaster.
Disaster, meaning the robots could end up, like, frozen, right? Not knowing which move to make.
Exactly. And that's what the researchers are calling a decision deadlock. The robot's just stuck there, can't decide whether to run or help its buddies. Not a good situation to be in.
Yeah, not ideal at all. So how does this paper propose to solve this whole decision-making dilemma?
Well, they've got a pretty clever solution, blending a kind of classic rule-based system with some machine learning magic. It all starts with something you might be familiar with, the finite state machine, or FSM.
FSM, okay, so
Yeah.
like a flow chart that tells the robots what to do.
Yeah, kind of. Think of it as a set of states the robot can be in and rules for switching between them. So if this happens, then do that, like a basic decision-making guide.
Right, a set of instructions. But I have a feeling there's a but coming. Like traditional FSMs probably aren't enough for, a crazy swarm battle.
You're sharp. The problem is, traditional FSMs, they're a bit rigid. They can't really handle all the crazy changes and surprises you'd find in a battle. That's where this paper comes in with their probabilistic finite state machine, the PFSM.
Okay, now things are getting interesting. What's the secret sauce here? What makes a PFSM different?
Well, the key difference is in the transitions. Instead of strict rules for the next move, the PFSM uses probabilities. So, like, each possible action has a certain chance of happening based on what the robot's sensing and what it's learned.
So it's like the robot's weighing its options, making a judgment call based on the situation, not just blindly following rules.
Exactly. And to make those judgment calls, the researchers bring in deep convolutional networks. The kind that power facial recognition and all that.
Oh yeah, those are pretty powerful. But wait, they're not just recognizing faces here, are they?
Definitely not. They're using them to analyze the whole battlefield situation. The paper describes this compound convolutional network, and it takes in three main streams of information.
3 streams, okay. Break it down for me. What kind of info are we talking about?
All right, so first, there's the agent-specific data, like the robot's own position, how fast it's moving, that kind of stuff. Then there's data about its teammates, where they are, what they're doing. And here's the cool part. They use this thing called attention weighting.
Attention weighting, huh? Sounds like the robot's figuring out which teammates to, actually pay attention to.
Right. It's like, imagine being in a crowded room. You can't focus on every voice. You got to prioritize. It's the same idea here. And finally, you've got the enemy data stream. This is all the info about the opponent, their moves, and so on.
So it's like the robot's getting this 360-degree view of the battlefield, its own status, what his buddies are up to, and what the enemy's doing.
Precisely. And all of that info gets fed into the convolutional network. Then it generates this thing called the transition probability matrix for the PFSM. That's like a dynamic roadmap for decision-making, always changing based on the situation.
All right, so far so good. This is starting to sound like a system that can actually handle the craziness of swarm combat. But how do they actually teach the robots to make good decisions?
That's where reinforcement learning steps in. They use a specific type called proximal policy optimization, or PPO, along with something called an actor-critic architecture.
PPO, actor-critic, a lot of jargon here. Can you break that down a bit?
Okay, so think of it like training a dog, right? The actor makes the decisions, the critic tells it how well it did, and the dog, or our robot in this case, learns from the rewards and corrections.
So the actor does stuff, the critic judges, and the robot learns. Got it. And this PPO thing, what's special about that?
Well, PPO is really good at finding the right balance between trying new stuff and sticking to what works. It's like exploration versus exploitation.
Huh.
And it's also known for being pretty stable and efficient.
Makes sense. So they're using this PPO to optimize the PFSM, those probabilities we were talking about.
Right, so the algorithm learns how to adjust those probabilities to give the robot the best chance of success in the battle.
It's like the robot's not just learning what to do, but also how to adapt its game plan as it goes. Pretty neat.
Exactly. It's all about becoming more adaptable and strategic. And to guide this learning, they use a specific reward function. It's like setting goals for the robot to achieve.
So not just winning at all costs, what are they aiming for with this reward function?
Winning smartly. They actually penalize things like those decision deadlocks we talked about, when the robot gets stuck. And they reward cooperative behavior, encouraging teamwork.
Okay, so they're building a team of robots that actually work together, not just a bunch of lone wolves. This is cool, but did they actually put this system to the test? Does it actually work?
Oh, yeah, they definitely tested it out. They ran simulations, and they even did some real-world experiments.
Real robots, huh? All right, I'm all ears. What do they find?
Well, in the simulations, their system was consistently better than other approaches. Even with a large number of robots, the ones using this new system had much higher win rates.
So they were actually coordinating, outsmarting their opponents.
Exactly. And they didn't just rely on brute force. The researchers actually visualized the decision-making process and found that this PFSM DRL system actually led to more cooperative behaviors.
So the robots were actually learning to have each other's backs. It's wild. But what you said, real robots too, right? Did they build a little robot battle arena?
Well, not quite a battle arena, but it was pretty close. They used 6 of these unmanned ground vehicles, or UGVs, split into 2 teams, red and blue.
Red team got the new system, I'm guessing.
You got it. The blue team had the traditional FSM approach with those fixed rules, while the red team had the fancy PFSM DRL system, and the results were pretty clear.
Red team dominated.
Dominated is putting it lightly. They even caught the blue team getting stuck in those decision deadlocks, not knowing what to do.
Yeah.
Meanwhile, the red team was adapting on the fly, exploiting those weaknesses.
That's amazing. It sounds like this research is a huge step forward for autonomous systems. It's pretty mind-blowing stuff.
Yeah, this paper's definitely got me thinking. It's not just theory. It's a practical solution with a lot of potential.
Speaking of potential, I'm curious to hear what kind of novel notions this research has sparked for you. It's time for our favorite segment.
All right, let's dive into the novel notions zone. What if we took this concept of a probabilistic state machine and applied it to human-robot collaboration?
Human-robot teamwork, huh? Now we're talking. But what would that look like? Paint me a picture.
Imagine a disaster relief scenario, right? A team of robots working alongside humans in this totally chaotic environment. They need to be able to adapt to anything, understand what humans are trying to do, and work together seamlessly.
That's a lot to ask. How could a PFSM help with all that?
Well, the PFSM could give robots the ability to make flexible decisions based on what's happening around them and what the humans are doing. It's about moving beyond just following instructions to being more like a partner, understanding human behavior.
So instead of being programmed for one specific job, the robot could figure out how to help in any situation, working with humans more naturally.
Exactly. Imagine a robot sees a human struggling to lift something heavy. The PFSM, combined with some sensors, could trigger it to switch into a helping mode and lend a hand without even being told to.
Wow, that would be incredible. It could totally change how humans and robots work together, especially in those high-pressure situations. Disaster relief, space exploration, who knows what else.
Yeah, the possibilities are huge. Using PFSMs for human-robot collaboration opens up a whole new world.
This has been an incredible deep dive. It's mind-blowing to see how machine learning is being used to tackle these complex problems. But before we get too carried away, just a reminder for our listeners that these novel notions are just that, ideas for the future.
Right. We're just exploring possibilities here. They're fun to think about, but no guarantees about when or if they'll become reality.
All right, listeners, time to get those brains working. Do you think we'll see robots using probabilistic state machines in the real world, working side by side with humans within the next 5 years? Let us know what you think in the comments.
And if you want to dive deeper into the technical stuff, we've got a link to the full research paper in the show notes.
And that's it for part 1 of this deep dive. We'll be back soon to explore how this research fits into the big picture of machine learning history. Stay tuned.
See you then. Thinking about how machines make decisions, it's really fascinating. This paper, with its PFSMs, it's pretty cutting edge. But it didn't just come out of nowhere.
So time for a little history lesson. Take us back to the beginning. Like, how did we get from basic computers to robots that can make, complex decisions in these crazy environments?
Well, we could go way back, but let's focus on those early rule-based systems. Remember expert systems back in the 70s, 80s?
Vaguely. Those were systems designed to, like, mimic how human experts think,
Yeah.
right? In specific fields.
Exactly. They used a ton of if-then-else rules, basically taking a human expert's knowledge and putting it into code. It was a big step, but they had their problems.
They were pretty inflexible, right? Like, if something unexpected happened, they wouldn't know what to do.
Right. Like a chef who can only follow a recipe, change one ingredient, and they're lost. That's where finite state machines, or FSMs, came in.
So FSMs were like the next generation, a better way to handle decisions.
Yeah, exactly. FSMs gave us a way to manage more complex decisions, especially for things with a bunch of steps, like controlling traffic lights or designing circuits. They were perfect for that.
Okay, I see how FSMs were a big improvement. But like we talked about before, they can be a bit rigid, especially in those unpredictable swarm battles.
Right. And that brings us to what's new in this paper. The probabilistic finite state machine, or PFSM. It takes the FSM idea and makes it, well, better.
Better by adding that probability element, giving the robots a little more wiggle room.
Exactly. Instead of those strict if this then that rules, now they can weigh their options, make decisions based on like how likely different outcomes are. It's a move towards more nuanced decision making.
This whole idea of thinking in probabilities, it's a big part of modern AI, right? Like self-driving cars, they're basically doing that all the time.
Absolutely. They're not just reacting, they're thinking ahead, predicting what other cars might do, and adjusting their course. It's a whole other level of, intelligence.
It's amazing how far we've come from those rigid systems to AI that can actually operate in the real world, adapting and making decisions.
It really shows how creative people are, constantly pushing to build smarter machines. And speaking of smarter machines, we can't forget about deep learning and its role in all this. Those convolutional neural networks, they've really changed the game.
Oh, yeah. Those are fantastic at recognizing patterns and picking out important features. It's like they see the world in a way that older algorithms just couldn't.
Exactly. And that ability to understand complex data, it's crucial for making smart decisions. It's not just about rules anymore. AI needs to learn from data, adapt to new situations.
Which is where reinforcement learning comes in. This paper uses that proximal policy optimization, or PPO. Can you give us a quick reminder, what's so special about PPO?
Think of it like teaching a dog a new trick, right? You give it rewards when it does well, corrections when it messes up. PPO is really good at finding that sweet spot between trying new things and sticking with what works.
So it's like the algorithm is playing around, trying different actions and learning from the feedback.
Right. And PPO is known for being pretty stable and efficient, which makes it a popular choice for training AI.
So in this paper, they're using PPO to fine-tune those transition probabilities in the PFSM. Like they're tweaking the robot's decision-making process based on the feedback it gets.
Exactly. The algorithm is learning how to adjust those probabilities to give the robot the best shot at winning the battle.
So it's learning what to do, but also how to adapt its strategy. That's impressive.
It really is. This combo of PFSM and PPO is a big part of what makes this research so innovative. It's a system that's both adaptable and tough, able to handle the craziness of swarm confrontation, but also learning and getting better over time.
This is all very cool, but we have to be real, right? There must be some challenges, some things that make it tricky to actually use these systems in the real world.
Oh, definitely. It's not all sunshine and rainbows. One of the biggest challenges with these complex AI systems is interpretability.
Okay, interpretability. Meaning, what exactly?
Well, deep learning models, they're powerful, but they can be like black boxes. We see what goes in, we see what comes out, but it's hard to know exactly why the AI made a certain decision.
So it's making good decisions, but we don't really know why. That could be a problem, especially if, people's lives are at stake.
Exactly. That's why there's so much research right now on explainable AI, trying to find ways to look inside those black boxes and understand how the AI is thinking.
Makes sense. Transparency is important, especially with powerful AI systems. Are there any other hurdles we need to think about?
Another big one is data. Deep learning models need tons of it to train properly. And sometimes getting that data is hard, expensive, or even impossible.
So it's like trying to feed a hungry monster. These AI models are data hungry, and it's not always easy to keep them fed.
That's a great way to put it. That's why there's a lot of work being done on making AI models more efficient so they can learn from less data, maybe even learn continuously from new experiences.
Like teaching the AI to be more resourceful makes sense. But even with these challenges, the potential of AI is huge.
No doubt about it. This research is a glimpse into a future where machines don't just follow orders, but they learn, they adapt, they work with us to solve tough problems.
I'm excited to see where it all goes.
Hmm.
But for now, let's get back to those novel notions.
Yeah.
What mind-bending ideas has this research sparked for you?
All right, let's push the limits here. What if we took this probabilistic state machine framework and combined it with swarm intelligence?
Swarm intelligence. Okay. That's the idea that a bunch of simple agents like ants or birds can do amazing things together, right?
That's it. Imagine swarms of robots, each one making decisions with a PFSM, but also communicating, working together, using that swarm intelligence to solve problems that would be impossible for one robot alone.
That's a really cool idea. Taking the power of PFSMs and multiplying it with the collective intelligence of a swarm.
Picture this. A swarm of robots exploring a totally new area, like the bottom of the ocean or the surface of Mars. Each robot has its own PFSM, making decisions based on what it sees.
But they're also talking to each other, sharing info, changing their plans based on what the whole swarm is learning.
Exactly. They could map the area together, find dangers, even work together to get past obstacles that one robot couldn't handle.
It's like a superorganism. Each robot is a part of this larger intelligent entity.
That's a great way to think about it. And this idea could be used in so many fields, from disaster response to environmental monitoring, even construction.
I can already see it. Swarms of robots building structures, fixing things, or searching for survivors in dangerous places.
The possibilities are endless. And the really cool part is, this approach could lead to systems that are truly autonomous, organizing themselves.
So they could adapt to changes, learn from what happens, even repair or copy themselves.
It's a glimpse into a future where robots aren't just tools, but they're partners, helping us explore, discover, and solve problems.
This is incredible. It's clear that AI isn't just about making machines smarter. It's about pushing the boundaries of what's possible, working with machines to create a better world.
Definitely. But as we explore these possibilities, it's super important to be careful to think about the ethics, make sure these powerful systems are used for good.
You're right. We need to make sure they're designed the right way, that they align with human values, and that we have safeguards to prevent any accidents.
It's a responsibility we all share, researchers, policymakers, everyone. We need to have open conversations about the good and the bad of AI to make sure it benefits everyone.
This deep dive has been amazing. Not just the technical stuff, but also thinking about the bigger picture, what it all means for the future of AI.
I agree. It's been great exploring this research with you, thinking about all the possibilities it opens up.
Now, for part 3 of our deep dive, we'll bring it all together, discuss what this research means for the future of AI. Stay tuned. Welcome back to TalkTensors. We've been exploring this fascinating paper on swarm confrontation, taking a look back at how machines have learned to make decisions and, well, even diving into some pretty wild what-if ideas.
Yeah, it's been quite a ride, from those early rule-based systems all the way to these probabilistic state machines and deep reinforcement learning.
And we've seen how this research could change everything from, robot battles to how humans and robots work together. But let's zoom out a bit. What does this work mean for AI, like the big picture?
I think this paper really shows us that we're thinking about AI decision-making in a whole new way. It's not about blindly following rules anymore. It's about flexibility, about systems that can learn and adapt as they go.
So it's not just programming robots for one specific task, but giving them the tools to learn, to strategize, to make decisions in really complex situations.
Exactly. This research is a great example of combining those older approaches, like FSMs, with the power of deep learning and reinforcement learning. And when you put those together, well, the possibilities are pretty much endless.
And those possibilities go way beyond just robots fighting in an arena, right?
Of course. Think about all the areas where AI is already having an impact, healthcare, finance, transportation, even art and music. Imagine using these adaptable decision-making systems in those fields.
Okay, so we're talking AI that could personalize medical treatments for each patient, algorithms that can navigate those crazy financial markets, maybe even AI tools that help artists and musicians to be even more creative.
That's the idea. And this research, it's like a blueprint for how to build those systems. Systems that learn from data, adapt to changes, and make decisions that that could even rival human experts.
It's pretty exciting, but also a little intimidating, right? AI has so much potential, but we have to be careful about the risks too.
You're absolutely right. As we build more and more sophisticated AI, we can't forget about the ethics. We need to make sure these systems align with human values and that we have, safeguards in place to prevent any unintended consequences.
It's a good reminder that the future of AI isn't set in stone. It's something we're all shaping through our choices, our research, and the ethical frameworks we put in place.
Well said. It's a responsibility we all share, researchers, policymakers, even the public. We need to talk openly and honestly about AI, the good and the bad, to make sure these powerful technologies are used for the right reasons.
This deep dive has been incredible. We didn't just look at the technical details of this paper, but we also thought about what it all means for the future of AI.
It's been a great exploration, and I hope our listeners are leaving with a sense of both the amazing potential of AI, but also the importance of developing it responsibly.
Thanks for joining us on this journey into swarm confrontation, probabilistic state machines, and the ever-changing world of AI decision-making. And that's a wrap for this deep dive. Until next time, keep those minds curious and those algorithms learning.
See you next time.